Welcome to the final unit in MCV4U, and let me tell you, we are finishing strong. This unit is all about equations of lines and planes, but it's not just the kind of line work you did back in grade 9. This is vectors meets geometry meets structure. You're about to see how the language of vectors can describe entire lines, planes, and directions in space, cleanly, powerfully, and precisely. So what's the big idea? In algebra, you learned lines as things like y equals mx plus b, or ax plus bx plus c equals 0. In calculus, we think bigger. What if we want to describe a line using direction, movement, or position in space? That's where today's lesson comes in. We're going to learn 3 ways to describe a line, all of which connect beautifully. We're going to look at the vector equation, which shows us the line as motion, a starting point and direction. Then we're going to look at the parametric equation, which breaks that motion into its x and y over time, those x and y components. And lastly, we're going to look at the scalar or Cartesian equation, which brings it back to the familiar algebraic form that we've been using since grade 9. Why learn all 3? Because each gives us a different lens on what a line really is, a path, a rule, a direction, and depending on the problem, one form might unlock the solution faster than the others. This is where vectors stop just being arrows and start becoming equations, system, and tools we can manipulate. Today we start in 2D, but just wait. Once you master this, you'll be ready to take it to 3D space and even define planes. So let's get started by looking first at vector equation, parametric equation, and scalar equation in 2D. Let's start with things you already know. A lot of what we're going to do in this unit is going to build on what you already know. So let's write the equation of each line in slope y-intercept form and standard form. Well, if we take a look at these first two, we can see that it's pretty easy for us to calculate the slope. So calculate the slope. The first one starts at the origin and goes to a point 2, 3. So my run will be 2 and my rise will be 3. So the slope for that one is pretty easy. Rise over run, which is 3 over 2. For this one, we have 2 points. So now we're looking at this one here. We have 2 points. We're going to need to figure out the slope using those 2 points. Remember, y2 minus y1 all over x2 minus x1. So that gives me a slope equal to 3 minus 2 over 2 minus 0, or 1/2. Okay, so now that we know the slope, we can write them both as y equals mx plus b. So for this first one, we have y equals 3 over 2x. The y-intercept is at 0, so our b value is just equal to 0. For the second one, we have a y-intercept at y equals 2, so y equals 1/2 x plus 2. Now, for this last one, we know a point and we know the slope, so we would use point-slope form. Just as a reminder, point-slope form is y minus y1 equals slope times x minus x1. Filling in what we know, we have the point, -3, 4, and we have a slope of -1. So we have y minus 4 equals our slope of -1 times x plus 3. Now, we could write all 3 of these in standard form, and remember, the standard form of our equation is ax plus by plus c equals 0. And to do that, we just simply need to rearrange what we know. So for this first one, we would rearrange and we would get 3x minus 2y is equal to 0. For the second one, we would get x minus 2y plus 4 equals 0. And for this last one, when we expand and rearrange, we get x plus y minus 1 equals 0. So just as a refresher, what two things do we need to get the equation of a line? Well, we need to know the slope and a point or the y-intercept. Slope and the y-intercept, or a slope and a point, or 2 points, and we can work our way backwards. So what do we need? Really, the slope and the y-intercept. We're going to come back to this because the standard form gives us what we call the scalar Cartesian equation of a line, but we're going to come back to that in a minute. First, I just want to talk about this idea of slope. So let's go to this middle one here, where we have a line between 2 points, 0, 2, and 2, 3. And to move along this line, anywhere along this line, I can use my slope. I could say for every movement, I'm going up 1 and over 2, up 1 and over 2, up 1 and over 2. So I want you to recognize that we can use any multiple of the slope and still be on that same line, and that will give us all the other points on the line. So I know that my slope is 1 over 2, but I certainly could go straight from anywhere on this line using multiples of that slope. And that's an idea that we're going to lean into today when we start talking about the vector equation of a line and what that actually means. So in slope y-intercept form and standard form, we have equations that define all points xy on the line. A vector equation of a line is an equation that describes resultant vectors that start at the origin and end at some point on the line. In order to create these resultant vectors, we need a position vector that gives us a point on the line. So here we have a position vector that gives us some point along our line. Our position vector in this case is going to be what we call R naught, or this R vector with a little 0 beside it. We call it R naught, and it goes from the origin to some point at X naught, Y naught along our line. You can see I've got a line here in red that we have a couple of points on that line. And what we're doing is we're creating vectors that are going to allow us to create a resultant vector that's going to give us a little bit more information and let us have this vector equation of the line. So we've got our position vector that goes to a point on the line. That's R naught, and that goes to the point X naught, Y naught. We also need a direction vector that's parallel to the line. And this is where this idea of slope comes in. So we talk about this direction vector being parallel to the line. Here's my direction vector. Well, really what that direction vector is it's a line that's parallel, meaning it has the same slope, and it will run along the line from one point to another. We can change the size of that slope by multiplying it by some scalar multiple t that really will just change how long or how short that line segment is, but doesn't change the slope of it at all. So we have that. By adding that position vector and our direction vectors together, we get a resultant vector, which is this vector right here. This resultant vector R that has its tip on a point on the line, has its tip on the point of the line. By multiplying the direction vector by t, so we're getting some scalar value times the slope, the resultant vector R can have its tip at any point along the line. And remember, t is just a scalar value. Can be any value really. So let's take a look at what this actually looks like. We're going to pop over to GeoGebra. Okay, so here we can see I have my vector R naught. So we've got our position vector that goes from the origin to some point A on the line. We can imagine that there is my direction vector here that's equal to the slope times some scalar value to make a line segment. And then here we can see that we have our resultant vector R. Now, the resultant vector r is the resultant of our direction added to our position, and I can change where this meets by changing the value that I'm multiplying my direction vector by. So you can see that as I change this, the tip of my resultant vector still stays along the line, because all I'm doing is I'm changing the scalar multiple of the slope. So there's a couple of different ways that we can think about this. We could write it out really as just being line segment OP. So line segment OP is our resultant vector. That's our resultant vector is equal to our line segment or our vector OP. So OP ought plus our direction vector, which goes from P ought to P. P ought, P naught to P. So really what we're saying here is that we have our resultant vector R is equal to R ought or R naught plus some scalar value times our displacement. So it can be written this way, or it can be written as the vector equation of a line in two space where we have xy in square brackets because they're a vector is equal to our given point. In this case, our given point is just some point on the line that our position vector points to, x ought, y ought, plus some multiple of our slope parameter. We call that a scalar multiple of the slope times the actual direction vector. And we're going to think of that as slope. We call it a direction vector, but it's really just the slope. So we can imagine this changing the length of the direction vector t. It will move up. It will move the tip of the resultant vector along that line. And that's what I just showed you in GeoGebra. So the resultant vector OP is the sum of the position vector R naught, or OP in this case, plus some scalar multiple of the direction vector added together. And that's what we're going to use to solve some questions and some equations. Okay, so let's use this new vector equation of x vector xy, or my resultant vector, is equal to the sum of some point plus a scalar multiple of our slope or our position vector. We're going to call it slope, just as it relates back to our slope. So let's find the vector equation of a line that passes through -2, 7, having a slope of 2/3. Well, here's our point. Remember, we need a point and we need the slope. Here's our slope. And we can think of the slope as 2/3, but what does that really mean? Well, that's rise over run. And remember, the rise is the y value, the run is the x value. And if we wanted to write this as a point, we could write it, or as a direction vector, we could write it as 3, 2. So let's put this all together and let's create our vector equation. So we have our resultant vector xy is equal to our position vector, which is -2, 7, that's our point, plus some scalar multiple of our slope, which is 3, 2. Our x and our y value, our delta y, our delta x, and our delta y value. So we can think of this as starting at -2, 7, and we can go any multiple we want where we add 2 onto the y's and 3 onto the x's at the same time. It has the same ratio. So let's find another point on the line. And we can find any other point on the line by taking multiples of the slope or changing the t value. So let's make our t value equal 1. It really could have equaled anything, but 1 is going to work for what we're doing today. So if t equals 1, then our vector equation of the line will be equal to -2, 7 plus 1 times 3, 2. So really what that means, if we're breaking it down, is that our x value for this for this point where the tip of this resultant vector hits will be -2 plus 1 times 3, right? Because we've got 1 times 3, I need to distribute this into there. So we'll have an x value for the tip of this vector of 1. And we'd have a y value at the tip of this resultant vector that would be 7 plus 1 times 2. 1 times 2, that gives me a y value 7 plus 2 of 9. So we could say that the point 1, 9 is on the line. It's like saying if we start at -2, 7 and we go up 3 and over 2, we get to 1, 9. So we can say, therefore, point 1, 9 is on the line. Point 1, 9 is on the line. Another way to write the equation of a line is in parametric equation form. And really, what we've done here is we've taken the vector equation and we've separated it into 2 parts, one for each variable, and those are the components of the vector equation. Now, we would write it, this is it here in blue. You will see me sometimes do it like this without the box around it. And what we have here is that the x component of this, so x equals x naught plus at. X naught is the x component of the point that we have, and the x value of the slope, or that a value, times some scalar multiple t. Our y value, so y equals y naught plus bt, well, y naught is the y component of the point, plus the y value of the slope, which is our b value, times a scalar multiple. So let's put it into action. So what are the parametric equations of the line that passes through a point A, 0, 5, and B, -6, 3? So just like in grade 9, we need the slope and a point. The only difference is now that we call the slope the direction vector AB. So we know that our slope is really going to be our direction vector, and that direction vector is going to be equal to a line segment that's AB. So the direction vector is just AB. We've seen this before. AB is just the x's subtract the y's. So if I have, so let's figure it out. So I have my x's subtract my y's. So -6 minus 0, so -6 minus 0, and 3 minus 5. That gives me that AB, or my direction vector, is equal to -6, -2. So now we want to reduce the slope in the lowest terms possible. And if we want to think about this slightly differently, this is the same as saying that we have a slope of -2 over -6. Remember back to grade 9 math, if you left it like that, that would definitely not be a level 4 answer. So we want to reduce it and make it look a little nicer. So I know that I can reduce this to a positive 1/3. So really here, our slope, or our direction vector, is going to be equal to 3 and 1. So now that we've got that slope, or that position vector out of the way, or direction vector out of the way, we're going to use either one of the points and the direction vector m to get the equation. So in vector terms, our vector equation then for this will look like this. xy is equal to our position vector 0, 5. I'm just going to choose to use that one. It doesn't matter. We could have used either. Plus a scalar multiple of our direction vector, which is 3, 1. Now, the parametric equation just breaks that into its x and y components. So we could say that this will be equal to, so what are our x components? Well, our x components is our x ought value, which in this case is 0, plus our our a value from our slope, remember this is AB, this is x naught, y naught. Yeah, why not? Sorry. Okay, so we have our x naught value plus our b value, or our a value from our slope times some value of t, some scalar multiple. So that would be 3t. Remember, we don't have to have the 0 there. So this actually would just be x is equal to 3t. So x is equal to 3t. And we're going to do the same thing for the y value. So our y value of this line is going to be equal to our y naught, which is 5, plus our value of our y value or b value of our slope, which is just 1 times some scalar t. So this would be our parametric equation. Here's our vector equation, and here's our parametric equation. So let's take a look at an example. So I didn't have this one in the slide presentation. I apologize for that. I've added it afterwards. We're going to look at this one a couple of ways. So are the following lines the same? And let's look at this using this idea of our parametric equations. So if they are the same, they will be the same if they have the same scalar multiple t for both equations. So that will mean they're collinear. They're on the same line. So we can think about this then in terms of is there some scalar multiple that will be the same for both of them? So how I would set this up and how I would think about this is that I know that these values represent some scalar multiple of my slope. So really, at the end of the day, what I'm trying to determine is my direction vector for line 1, which in this case is -3, 2, going to be some scalar multiple of the direction vector of line number 2, which is 6, -4. Well, I think we can see that they are, but I'm going to show you how you could prove it if it wasn't quite so obvious. And how we're going to do that is we're going to say, okay, my x value then, my x value of d1 must be equal to some scalar multiple of my x value of d2. So we would say in this case then -3, which is my x value from d1, must be equal to 6 times some multiple of t. We can do the same thing with what we've got going on with the y values. So my y value for d1 is 2. And that's got to be equal to my y value from d2 times some scalar multiple. Well, rearrange and solve for t. So this is -3/6 equals t. Remember I said we want to reduce. So we're going to reduce this to be -1/2 is equal to t. Now let's look at the same thing for the other one. So now we have 2/4 equals t. Well, that does indeed equal -1/2. And so they're equal. So they are the same. So we've solved for t. If the scalar multiples are the same, then they're on the same line. They're collinear. We got the same value for each one. Therefore, they are on the same line, or they are the same. When we say the same, what we really mean is, are they on the same line? So now I want us to take a look at this using the vector equations instead of the parametric equations. Same question. Are the following lines the same? Well, we want to compare the direction vectors, the slope. If they are scalar multiples of each other, then they are collinear. They fall on the same line. We're going to set it up exactly the same way, except now it's a little bit more obvious to see what's what. There's our D1, there's our D2. The process is exactly the same. D1 is 3, -2. D2 is -6, 4. And we can see quite easily that these are scalar multiples, but I'd like to point out to you that there actually is a simpler way to determine this, and we could figure out what AB is. And so here's A, point A, here is point B. So what would AB be? Well, AB is just going to be, we subtract the x's, we subtract the y's. So I subtract my x's, I have 4 minus 1 for my x value. I subtract my y's, I have 4 minus 6 for my y values. So that equals 3, negative 2. We can see that we end up with the same slope. That means the points must be on the same line. I promised you that we were going to look at 3 different ways of writing these equations, and this is the last one for today. So we're going to look at the scalar or Cartesian equation of a line. This is the same thing as standard form from way back in grade 9. So we have it in the form of ax plus by plus c equals 0. So let's look at an example. So if I'm given a parametric equation of x equals 2t, and y equals 1 minus 3t, I would maybe write that a little bit differently. I'd write it one on top of the other, but at the end of the day, it doesn't really matter. Remember, when we've got it this way, anything times the t is our direction vector or our slope. So here's our direction vector. And the other 2 points, in this case we have 0 and 1, this here is my point or a position vector. So I can create the vector equation of a line quite easily. Once I know those 2 things, I have a point, 0, 1, plus t times my slope or my distance or my direction vector, which is 2, negative 3. 2, negative 3. So there's my vector equation of a line. If I want to turn this into a scalar equation, there's lots of different ways we can do this. I'm going to show you 3 different ways to do it. These are not the exhaustive 3, but this is what we're going to do. Now, I do want to point out that the scalar equation of a line, we can do this in 2-space, but we won't be able to do it once we move on to 3-space or 3D. Once we get into 3 dimensions, we're not talking about lines anymore. We're actually talking about planes, and we're going to talk some more about that in a little bit. Not today, in the next lesson. Okay, so there's 3 different ways we can do this. The first way that we're going to look at is using point-slope form or some other form of the equation, or some other form. And you're going to see what I mean here in a second. So if I'm using point-slope form, remember point-slope form is y minus y1 equals the slope x minus x1. Now, if I take a look at the information that I have in this equation, I have my slope and I have a point, but this point happens to be my y-intercept where x equals 0. So in this case, instead of using point-slope form, I would probably use y equals mx plus b. This might be easier since we know the y-intercept value. So let's fill in what we know. Well, we know the slope in this case is equal to negative 3 over 2, or our y over our x. We know our y-intercept, or our b value, is 1. So putting that together, we get y equals negative 3 over 2x plus 1. Now remember, it's not asking for us to put it into slope-intercept form. It's asking for us to put it into standard form, so we need to rearrange to get it into standard form. So we would have y minus 1 equals negative 3 over 2x, multiply both sides by 2, 2y minus 1 equals negative 3x. I'm going to expand that out. 2y minus 2 equals negative 3x. Let's bring this x over, and we end up with 3x plus 2y minus 2 equals 0. So there's our first way to take the vector form of an equation and turn it into a scalar equation, standard form. The second way we're going to do it is we're going to rearrange for this scalar multiple t And we're going to use the parametric equations to do that. So my parametric equations, as a reminder, x was equal to 2t, y was equal to 1 minus 3t. So that tells me that x over 2 is equal to t, and y minus 1 over 3 over negative 3 is equal to t. Well, we know that they're the same, so we know that they're going to be equal to each other. We'd have two values of t. We're going to set them equal to each other. So x over 2 is equal to y minus 1 over negative 3. Now we're just going to rearrange to get this into standard form. So we're going to end up with negative 3 times x equals 2 times y minus 1. So negative 3x equals 2y minus 2. So 0 equals 3x plus 2y minus 2. Now, there is a third way that we can take a look at these, and that's using this idea of the normal. And I want us to think about this a little bit. So the third option is using the normal. And remember from back in calculus that the normal is perpendicular to the tangent, or we can think of it as perpendicular to the slope. So let's figure out how can we determine the slope of our standard form ax plus by plus c. Well, we're just going to rearrange to get y by itself. So in this case, we would have y is equal to negative a over b, x minus c over b. That means that our slope in this case is equal to negative a over b. Well, we know that the normal would be perpendicular to this. So if you remember back to grade 9, if I know the slope and I want to know the slope of a perpendicular line, I invert it, so I flip it over. We take the negative reciprocal, so I flip it over and I change the sign. So negative a over b becomes b over a. I've flipped it and I've gotten rid of the negative. I've changed the sign. So we end up with our normal vector n being equal to b over a. Well, this is our y and our x. These are our coefficients of our standard form of our equation. These are our a, b values in our ax plus by plus c. So if we know the normal, we know the coefficients for x and y, and we just need to solve for c. So this is how we can do this. So we know that we have x is equal to 2t. So again, we're still in parametric form. Y is equal to 1 minus 3t. So if our slope is equal to negative 3 over 2, then our normal is going to be equal to, flip it upside down, change the sign, is going to be equal to 2 over 3. And we can rewrite that as the vector 3, 2. Now, we're going to sub 3, 2 for a and b in our equation. So we end up with 3x plus 2y plus c equals 0. Now we need to solve for c. The easiest way to do that is to just pick a point and sub it in. Well, we know the point. We have a point, and that point was 0, 1. We got that back here from the original vector equation that we created. So we've got that point. So we're just going to sub it in and solve for c. So 3 times 0, 3 times x, plus 2 times 1, which is our y value, plus c equals 0. So 2 plus c equals 0. So c equals negative 2. Now we have all the information that we need to put this together in standard form. We have 3x plus 2y minus 2 equals 0. Okay, that's going to be it for today. There are quite a few practice questions from the textbook. I encourage you to do as many of them as you possibly can. And as always, if you have any questions at all, reach out by email.